Good morning, good afternoon. Welcome to our next lecture on architectures of AI systems. Today I'm gonna talk about the model drift. It's a kind of the continuation of the previous lecture on the data drift. Now we're going to talk about what may happen with models in the situation when the reality changes. So just a small recap. As I mentioned previously, we have two different areas. One is for model experimentation and development, and the second one is just a production one. And previously we were talking about the data validation, just a check whether the data comply one with another on here in this training and validation stage, and secondly on the request level, the custom request level. Okay, but we focused on testing whether data complies with, for example, the training data, and what may go wrong with the data coming to our system, to our model, what may go wrong with the data in requests. We mentioned that the distribution of data inputs and labels may change. There may be a change in the schema. There may be a change in the relationship between features and labels. There may be some change in data source, for example, data sources maintained by others or an upstream model. Today we are going to focus on this aspect, the change in the relationship between features and labels, which in most cases is the consequence of the changing reality. Reality in the sense that, for example, our demand forecasting model might generate some errors because, for example, some new competitor becomes on the market, appears on the market, there is an inflation, there are the changing habits of the customers, etc., etc. So today we are going to focus on so-called model drift. In my previous lecture, I presented you with one of the most advanced open libraries on the market, TensorFlow Data Validation, which is the part of much larger suite, TensorFlow Extended. It's an open source solution developed by Google to manage whole ML DevOps systems. We have shown that it's possible to validate continuously arriving data. So, for example, we may generate some reference data, reference statistics for day 1 stats, and then generate statistics for day 2, day 3, and compare the statistics to the original ones using this validate statistics library to get validation report, and in case of any inconsistency, trigger an alert which may, for example, later on trigger retraining of the model or block the request of the batch of requests. So, moreover, we said that the steps are the following. Firstly, we generate statistics. Next, we generate schema. And finally, compare both results from the reference dataset and the tested dataset to identify some anomalies. So that was for the data validation, but now I will display the most common techniques and methods and techniques of finding whether our model drifts. So let's dive into. Our workflow will be the following. This is the workflow you are going to find in my course materials in the practice session. It is a text file where we'll have all those points expanded with some Python snippets with explanations and all the recommendations for you. The steps are the following. Firstly, we are going to generate some serving data. Next, we'll detect model drift, load score datasets, prepare data for test, define and perform test. Next, we will automatically generate retraining signal and run retraining script if model drift is detected. So yeah, this is the MLOps level 1. So the system which automatically runs the retraining process in case the model drift is detected. So this is our workflow. But now let's go to main methods. How to test whether the model drift? We have some different types of tests at hand. And the first one is the so-called HUD test. That's the simplest possible, very easy to understand. So we just set a minimum acceptable level of the model quality for example, binary classification that may be receiver operating curve area under the curve value or accuracy level. And we trigger the signal when the model quality measure exceeds this threshold. So, for example, if we set this level of accuracy as the minimum accepted, for example, by business level, then we perform on a daily basis the measurements of the quality of the model. And at some point, we may find that the model has the accuracy below the threshold, and in that case we generate the signal. This is the time axis here, so imagine that this is the week by week computation of the accuracy of the model. It may be done automatically by comparing the predictions for a given week with the actual values of actual reality. Yes, so that was the first one. The second test is so-called benchmarking test. So we generate the signal when the model quality measure is worse than all previous values. So the problem is that sometimes this test is too sensitive and the retraining signal is triggered too often and unnecessarily. So for example, now I changed the example from binary classification to regression using root mean square error measure, for example, for this. So imagine that we have in that case, the higher the model, the value of the error, the worse. So as you can see, in that sequence of measurements of the RMSE over time, we would have generated the retraining signal in that case. Why? Because it's worse than all the previous. In that case, once again, in that case, we wouldn't, because it's not worse than all previous levels, here not, and for example, we would trigger the signal here. So as you can see, this test sometimes may be oversensitive, so be careful with that. Sometimes it's used, but we need to be careful with that. So once again, the next method. As you can see, I present you with some qualitative methods. They're quite easy to program, and you will find that in my Python scripts. Next one, a bit more advanced, is so-called parametric signal. So in that case, we generate the retraining signal in a situation where the current value of the quality measure is worse, that may be smaller or larger by 2 standard deviations from the average of the previous values. So here on the right, you have 2 different situations. So for example, for regression and measures like RMSE or MSE, mean square error or root mean square error, the higher the error, the worse model is. So for example, if you have 100 measurements from previous days or weeks, so you can compute for them a mean, you can compute for them standard deviation, yes. So you will say, okay, I will trigger the training signal in case my current measurement is higher than mean plus 2 standard deviations. Okay, so on opposite, when we have the measure like accuracy, precision, ROC, IOC, which is worse if it's lower, we have the very similar procedure, but we'll trigger the retraining signal in case the value of the measure is lower than mean minus 2 standard deviation. So the procedure is simple. You take all your previous measurements, you calculate the average of them, you calculate the standard deviation, you check if the current measure value is worse, smaller or larger than the mean plus minus 2 times standard deviation. Problem: sometimes our quality measure readings do not follow a bell curve because, for example, outliers, and that method may fail. So this is the next method, parametric signal. We may have also non-parametric tests like outlier detection. So a small recap of the simple statistical method for outlier detection of a single variable. In that case, we generate the retraining signal in case the current value of the quality measure is interpreted as an outlier and is worse than the previous values. So once again, just a small recap, the procedure is the following. For a set of previous measures, calculate the first quartile. It is here, yes, so this is this is the statistics of our previous historical measurements of our quality measure. So for such a sequence of numbers, we may compute the first quartile, we may compute the third quartile. Next, basing on them, you can compute so-called interquartile distance, IQR, which is that length. So basically it's third quartile minus 1 quartile. And then next we determine the limits of normal values. Okay, so normal values mean not outliers. And we identify the lower limit for this as Q1, first quartile minus 1.5. That's the status quo, yeah, so 1.5 times IQR, this 1.5 times IQR. Next, the upper limit, that way. And for the new model quality measure, check that it is within acceptable limits. So measurement is normal in that case. Generate a post-training signal when the new value of the measure is outside those limits and is worse than the others, smaller or larger depending on the type of the measurement. Okay, so as you can see, for measures like mean square error or root mean square error, where the higher value of the measure means the result is worse, yes, we trigger the training signal for that values, and for measures like accuracy, precision, recall, or receiver operating curve, area under the curve for that case. So once again, quite simple formula, quite easy to be computed, extremely fast in computations because we just simply cope with simple numbers, so it's immediate. So this is non-parametric test using outlier detection. So that concludes all the most methods used in model drifting. Obviously, they can be quite easily implemented in the Python code. And now it's your turn. Do your best, try to implement it in your codes. Thank you.